But this afternoon, it's my pleasure to introduce Dr. Robin Murphy, who's Raytheon Professor of Computer Science and Engineering at Texas A&M University. And Robin is, as you might see from the abstract, is one of the founders of the field of rescue robotics and robot-human interaction, and has been working with robots in disaster situations for many years. And one very nice, among many awards, Robin has recently received the Eugene Lawler Award for Humanitarian Contributions to Computer Science. And so it's my great pleasure to welcome Dr. Murphy.
Thank you very much for having me here today. And I'll be talking about disaster robotics. I'll be focusing on human-robot interaction because disaster robotics is less about the robots and it's more about the human-robot interaction, and in particular the informatics, how people get the information they need to make important decisions to save lives and to speed economic recovery. And in particular, I'm going to talk about 3 different methods that we use for capturing HRI: viewpoint-oriented cognitive work analysis, field ethnography that we've sort of formalized, and computational model of the data to decision process. So I'm going to tell you just a little about Texas A&M and explain what disaster robotics is, how we conduct field ethnography, how we model distributed decision makers, and then I hope to see if you're interested in participating in our Summer Institute. So if you're not familiar with Texas A&M, if you were in fire rescue or public safety, you would know Texas A&M's name. If not, you know, that's not something that we as academics really know much about. It is a huge leader in disaster practice. Disaster City, the Riverside campus, we train about 280,000 people a year in all aspects of fire rescue and law enforcement, emergency management. We own Texas Task Force 1, the FEMA team. We train all 28 FEMA teams, so it's a big deal. We're also a top engineering school. We're 3rd in the USA with research expenditures, just behind MIT and Georgia Tech. I've written a book, and it was through 2012. It documents 34 disasters. 13 were from the Center for Robot-Assisted Search and Rescue, which I direct, and it's now up to 18. It has data, if you're interested, on the types of robots and missions and things. So I'm not going to talk as much about those types of things, but it's just in there. The Center for Robot-Assisted Search and Rescue is interesting. It's not really an academic center. It got started to try to use some robots that have been developed for DARPA and was started 2 weeks before 9/11 to use for disasters. So the timing was creepy, very, very prescient. And we've always done this process of trying, no academic group can keep up with the best technology. I mean, your robots are really computers, right? Who's got a 10-year-old computer that they use, really? You know, or a 10-year-old phone. They're changing constantly. So no group can keep up with that kind of innovation. So we work with industry to get them and train them to go with us to disasters. And by the way, I am trying to, the fact that I am still going to disasters, and at this point it looks like I may go to Nepal, is a failure, because these are, I'll talk about later, these should belong, they should be routine in all of the fire rescue departments and the UN teams. So this is a disappointment that this many years after 9/11 we still don't have them there. All right, but anyway, we work with great, fantastic companies. I also wear a second hat that is more the traditional academic sort of center. This is the Center for Emergency Informatics. It's a center of centers that focuses on the idea that we have wireless network people that are working with the FirstNet, the LTE network that will be solely for responders. We have groups that are working solely with chemical process safety, these types of things, railroad disasters, the bridge school who knows about all the regulations, and how we pull them all together so that the idea is to get the right information to the right person at the right time. And of course work with TEACs, the people who are in Disaster City. So what are disaster robots? Well, let's just kind of go through what some of them look like, and these are the ones that I showed you mine because I own the rights. We own the rights to that video, so it's easier. The very first use of robots was the World Trade Center. Ground robots were used quite successfully. You're seeing as they go through, you're seeing they're kind of small, about the size of a shoebox. 2005 was the first use of UAVs, either fixed wing or aerial vehicles. That's surface vehicles. Think about how much of 80% of the population lives by water, so that underwater infrastructure becomes really important. We've been in several mine disasters. Very different. Building collapses, that's a parking garage that collapsed. That's actually a caterpillar robot, not a snake robot. It works like a caterpillar, but instead of scrunching its way up like a long-haired caterpillar goes, it vibrates. But with the Velcro hair, it does the same thing as if it's scrunching it, so it can get really small spaces. I was not at Fukushima, I was in Tokyo helping design the protocols for using that Honeywell T-Hawk, and the videos were much better. TEPCO down-selected those, sampled them. We came twice to work with the tsunami. You'll see more video from that. So those are what underwater robots look like. And tethered, the ROVs are tethered, the square ones. That is not a hand. We all thought it was a glove. And so you're seeing the idea of sensing and acting just by touching. You can figure out what you're looking at a little better. The mudslides up in Osa, we flew during the original mudslides. We went up for the third day. We were invited up, but they got canceled by another part of the county for privacy. Then they brought us about 2 weeks later, and then we came back last summer, and we expect to go back this summer to finish up the hydrological study of how that's working. So what are disasters and humanitarian relief type stuff? So an incident is kind of a routine disaster. Does that make sense? It's a routine emergency, but it normally doesn't exceed local resources. A disaster is defined as exceeding local resources, so it's a little bit out of the norm. Now, if you look at disasters, there are lots of different ways to do the phases of disasters. And this apparently, if you go to a conference with emergency managers, they will fight about this. But let's just use this one for now. The idea that you've got before the preparation and prevention phase, that's before something bad happens. Immediately after something bad happens, you have to mitigate whatever is bad. You have to respond to your life-saving response. And usually you start your big infrastructure recovery, like if you've got a levee broken or something like that. Okay, so that's one set of phases. And then you have another set that goes sometimes in parallel, sometimes after. It's better if it's in parallel. Faster is humanitarian relief, which is what you're seeing a lot. Let's try to get food to individuals. Let's give individuals houses, temporary shelters, which I was told by the World Bank this morning that we don't like to use that name. Right? So disaster robotics is mostly focused on this mitigation response recovery. Really the first couple of weeks, couple of months associated with a disaster. And you can further divide it into urban, which is like if you have a building collapse, something like the World Trade Center or that set of buildings in Cologne, Germany, or you have wide area, which is like an earthquake or Hurricane Katrina, very, very big. And we're also doing more now with medical disasters like the Ebola, but I won't be talking about that. So what's really kind of scary, and this is holding true for the Nepal earthquake, is that there's about a 4.7-day average delay in using robots. Any kind, land, sea, or air, getting them out there. And some of the reasons is that if the agency owns the robots, or someone that they have an emergency mutual aid compact with owns it, they're there, they're using it, exactly what you want it to do. Otherwise, they have to go find them, they have to transport them in, they have to figure out, they get through that first wave of chaos and the disaster, and then they say, oh wow, we need this, and so it takes days. And you see what happens with that when you have nothing. But the good news is that despite those kind of terrible numbers, they've been used in 43 separate events, 44 with Nepal. And you can see they're kind of evenly spread. The UAVs are coming up in popularity. The marine vehicles, given that 80% of the population lives by water, should be probably more. And they've been in now 14 countries. So it's not just a US phenomenon. So here's what the ground robots look like. Mostly we call them UGVs. You saw, again, they're pretty small. That's the one about the size of a suitcase. That's later on when we're in the recovery phase. Again, it's a shoebox-sized robot, almost always tethered. In fact, I actually know of no case where a robot's actually been run untethered because of the, Fukushima, they were primarily tethered with fiber optics because they couldn't afford to lose wireless, and it's unpredictable when you're in that kind of environment. Aerial vehicles, they come in two styles, things that look like helicopters or quadrotors, and things that look like planes, only smaller. And one of the nice things is that the planes can fly, over longer distances, and the helicopters are hummingbirds, right? You can look up and down and get very specialized views the structural engineers love. And in particular, that's what UAVs have traditionally been used for, rapid things. So that's some of Hurricane Katrina, some of the damage there. We're working with insurance companies on how to use this. So imagine the search and rescue teams being able to use this and at the same time share the data with the insurance company so they can start making it, and then share it with the American Red Cross, who, by the way, comes through and tries to estimate the damage so that they can estimate how long people are going to be homeless there. And so you see, this is post-Katrina when we came back and flew from there. Let's see that. So we've seen some of that, so we'll go. And here's with the marine vehicle. And that's the mudslide. So this is kind of fun. And the video is fun. Certainly the mudslides are not. So typically you get a low resolution view that you're seeing now, and then when it takes a picture, it's taking a high resolution image. You can see that, and then it stitches it together back when you land. You take the SD card out, you stitch it together, and it'll take anywhere between 3 hours and 24. And you can get a digital elevation map, a surface map, those sorts of things. So we'll just move on. Okay, in the marine vehicles, you've got ones that can be on the surface, so you're talking about robot boats. And you've got things that look like squares, those are the ROVs, the underwater. And then the autonomous underwater vehicles are not very smart. You think of autonomous as being really smart. No, they're just basically going off of the attitude if you program them to go straight underwater for a certain period of time, they probably won't hit anything and the fish will move out of the way. And that's pretty much true. And then when they surface every now and then to do their little radio link to the satellite, they have big things painted saying, please do not pick me up. If you pick me up, call this number, because people always in boats always go over and pick them up. But see, look at that kind of thing. This is going underneath one of those floating houses where a person, bodies may have been, victims may have been trapped under there in the tsunami. And they had, in that particular area, that's Minami Senriku, they had, that's a boat, or a car in that particular one, a car. And there's the view of the car from the sonar. And then when you get close enough to see, you had to be 6 feet away. The water was so turbid in Japan. But they had over 1,000 people still missing, and so they were very concerned with their loved ones out in the bay. So we were there for infrastructure and then doing a lot of victim recovery work. So the trends that you would see there, so thinking about this from a larger view, is that the robots were generally small in size. So they're not like the Predator types, and they're not the big Hurt Locker types of robots that you've seen. And that's because the responders can carry them. That solves a lot of your logistics problems. That helps with that 4.7 day problem. That means something they can have with them. They don't have to ask permission. The National Guard will provide a Predator to any disaster, but you have to ask, and then it goes to this chain of command, and you've lost 2 days right there. All right, so and that gets that idea of organic and tactical use. It means it belongs to the people who are trying to get the immediate data for them. And they're commercially available. I don't take robots to the field that have not been tried, because you can actually make a disaster work. There's been a couple of cases, the Pipe River mine disaster, the robots there actually blocked any human entry. When you have something that weighs a half a ton, that's not a good thing to go bad. All right, so, but on the other hand, you might be thinking, wow, if you're using military robots or robots that are used for inspection services, well, where are we going to go with human-robot interaction? How is she going to make a whole talk out of human-robot interaction? Because don't they have that solved? And the answer is no. So about 1999, we began to notice, as we started working more and more in the field with Florida Task Force 3, I was in Florida at the time, the robots just didn't seem to work that well. Even the military was like, oh, this is all great. And that was, we were in Tampa, right next to the SOCOM. Oh, this is great. Well, first off, the military missions don't really map over to fire rescue. So the things that you want to do. So like that Honeywell T-Hawk they were using at Fukushima to do radiation surveys and structural surveys, what they had previously used it for was to go look for a bad person in a car in the middle of nowhere in Afghanistan and track them. That's way different than flying next to a building and surveying for radiological damage and doing your radiation survey and doing your structural assessment and hoping that the radiation wasn't bad enough to knock it out of the sky. So they, we weren't seeing that things like that don't map over. And we also have a heuristic that about 20 minutes of operating any of these robots is about 2 hours of cognitive load. So after you do this for a couple of hours, you are dead. You are wiped for there. And the inspection protocols, the stuff that they do in inspection is like, oh, well, you do this, and then you stop and look around, and then you do this. So it was very, very slow, not well suited for this is a disaster, hurry, hurry, hurry. So that wasn't working well. And then we got the weird stuff. Now, this was the one that really was scary because the whole thing in robots is robots are to replace people, right? Worse, we found it just looked like if we had 2 people, it just went faster and it was more reliable and more trustworthy what we were seeing. And that actually was making the problem worse. We're supposed to have no people, and now we're seeing 2 people. And this caused me problems with funding with the Army. All right, so, and then later on we began to, as we were able to get more data, 50% of the mission failure. So if you did have a mission failure, which wasn't that common, so let's not, 43 disasters, there's only been 13 that they've had a run where the robot failed. It was considered human failure. And we'll talk about that. So let me go through now a little bit of how we came to those conclusions and started to tighten up those observations that we saw, because they all turned out to be pretty much accepted now. We realized that these were new types of uses, that these were not, robots don't replace people, you're using aerial, ground, marine vehicles in ways that people, responders have never had to use. Well, one way if you're doing automation to try to do something, you would do task analysis. Take how the person does it now, create a machine to do it that way. Remember, there's going to be some loss, not perfect matching, fix that part, and then we're good to go. If you don't have that list of what people do because they aren't hummingbirds, then you've got a problem, right? So how do you work, with that? And so there's a technique by Kim Vicente at Ohio State called cognitive work analysis, and it's specifically for formative environments. And what's nice, which is where you don't, which formative environments, in engineering speak is, we don't know what we're doing. Right, so it's an innovative environment. So we took that and started using that. And in particular, you see in cognitive work analysis, you use several techniques to try to get basically these 5 questions. What's the work domain? Can you tell me what the environment, the overall ecology is? What are the control tasks? What are the main things they're trying to do? Are there any strategies that they have to do? Do you have to use a wireless? Do you have to do this? Is there some, those types of things? What's the social organization and cooperation? That actually turns out to be critical. How do they work? What's their current work practice? It's always helpful to know to design a system, what the enterprise is. And what are your worker competencies? And one of the first things we noticed is that the military on the worker competencies is happy to spend 52 weeks to train somebody how to use a robot. The fire rescue teams they think 40 hours is a big deal. 24 is about all they're willing to cover, and they're not happy with having to put that in like every month. Now you think about it, all these teams, all these firemen, do you think if there's any fire department in the world who has extra people? everybody's pretty much working 100%, so they can't really absorb much. So that was one of the things we found. Well, we also changed cognitive work analysis up a bit to viewpoint oriented. And one of the first things we started doing is to try to figure out these relationships and what people were really doing. The first thing is, where do people stand? Where do they want to stand, or in some cases sit? And what do they look at? Because that's going to tell you how they're interacting with each other in the team. And so here's a great example of where do they stand. So here they're controlling a UAV. Here's the screen. Notice the screen right here. Small screen. All small screens are small because it makes it easier to carry. We're doing a visually directed task. Small is like the worst possible choice, but yeah, but let's add bright sunlight to just make it more complex. But we'll make it more fun because we're going to have the person who knows how to fly the plane versus the person who actually knows what we're looking for stand really close to each other. Okay, preferably let's try to bump the operator. Not that that's ever happened before. Okay? Okay, notice Thomas in the middle.
The use of jargon emerged naturally.
So you see the Steve right there is like pointing. He didn't even notice. Thomas, the operator, the pilot, there's no way he saw him do this, right? You know, his eyes, because he's heads down trying not to hit the power line he's flying next to. Okay. Meanwhile, the other guy, you don't see it, has actually pointed that way, like either of the other two people could have seen that. You know, and there's stuff. So, you know, no, let's fix that. So that's one thing. So where they stand and what do they look at? They're looking at the same thing. They're standing way too close. But let's look at where they'd want to stand. In general, you would prefer to have the person, Steve would be just as happy to be in his SUV running the entire response as are back at the EOC, right, where you've got the multiple screens and that, where to coordinate. So they actually don't want to be next to the robots. They're, you know, the first couple of times, yeah, because they're kind of cute, but you know, in real life, they got things to do. They want to be running other things. So one of the things we took, so this is just a little braggy thing, is that they created this program, this interface.
When unmanned aerial vehicles are deployed for use in a disaster, success depends on a team of people working together. At a minimum, this includes a pilot, safety officer, and mission specialist. Additionally, off-site experts may be stakeholders in the operation. Each stakeholder is interested in something different and ultimately must convey their needs to the pilot without disrupting safety protocols. Skyrider is a collaborative, unobtrusive communication medium that augments the UAV pilot's traditional display with requests from other team members. Skyrider is available to team members via any modern web browser and works on both local and remote devices. Skyrider allows team members to view flight details and communicate their needs by sketching on the UAV video stream or by using the spotlight feature to indicate areas of particular interest. Additionally, Skyrider can be customized to provide team members with information like a satellite view of the UAV's current location or onboard sensor readings. The pilot and all other team members are able to view sketching and spotlights in real time. If working in an oversight mode, the pilot can acknowledge and clarify requests from team members through sketching on their own interface. Alternatively, if the pilot is engaged in manual control, verbal feedback can be used. Early trials of physical world simulations of disaster response missions have confirmed the pilot's ability to use Skyrider without incident and have generated several questions for further investigation.
So that was one of the props, two of the props at Disaster City. We've got a complete chemical train derailment and a passenger train derailment, and then we've got a multi-story building collapse like the Murrah building in the World Trade Center. So anyway, that gives you an idea of some of the things that you get out of that. So if you're going to be working together, you need to look at stuff. Now they can work at a distance. So why is it doing this again? Let's move along. All right. So another thing that we did, so that's cognitive work analysis, and that's one of the things that came out of it, is that Skyrider interface. Another thing that we've had to do is field ethnography. We go to disasters to learn. That's a big thing. So here's what we recommend people collect, roboticists collect, of anything in the field. You want to get the log of the activity, context video, which is Their robot, whatever the robot was sensing, whatever the state was, the external view. Basically, we put a GoPro. If it moves, it's got a GoPro stuck to it. And then there's some extra things we do. We either do the ethnography by journaling in an after-action report, or if we're running an exercise, we have observers actually trained to do the ethnography and try to catch what's going on. I'll give an example. All right, so this is field ethnography, which often consists of me conveniently journaling whenever somebody has something heavy to lift, is what my students have accused me of, but this is over in Japan, trying to keep up with their. Now, when we do it in the field, we train, you know, one of the problems with ethnography is it tends to be qualitative, not quantitative, and depends on the skill of the observer. And there's lots of things we should do. We should be doing Cohen's gap, all that. But to try to make it faster, to be more consistent, we've developed this worksheet for the observer who just stands and watches, doesn't say anything. So based on the role, like the operator, the mission specialist, whoever, and we check off where they just do little tick marks. When did they seem distracted? Check, check, check. Did they make mistakes? Oh, they did. They both were confused and hesitant. Did they ask questions? You know, the slips and mistakes are classic of HCI ideas of error, but these other things are also indications to us. And even with all the military investment, we still get ergonomic issues all the time that show up. And so even though this seems kind of trivial, you can get a lot out of it. So here's an example of where we were doing we had a radiation source, a small one. I mean, you've had to sit on it to cause any problems. A cesium source that's basically radioactive for about a day in Disaster City, and it's in a blue canister about this big, which you would think that nobody would be able to miss, and it's in a space about this big, right? And we sent a robot in, and the operator couldn't find it. I think it took them like 30 minutes. I mean, it had to have driven over it at least 3 times. And the observer noted that the operator kept complaining that the radiation readings just seemed more consistent when the robot was going backwards, which was just totally non-intuitive. Well, we had an extra undergraduate that summer, so we said, well, go track this down. You know, because we were thinking, I was thinking it was human error. That seemed, you know, reasonable. Tanner, the operator, felt hurt, but whatever. But we sent a student to go work on it. He pulled everything together. Lo and behold, they were right. The chassis was actually blocking the radiation sensor. The radiation sensor is basically omnidirectional, but if you put it up against a piece of metal, it becomes directional. Okay. You know, and so who knew? So I called over to the Japanese Atomic Energy Agency. We've got an MOU with them, and I said, have you ever seen this? They were like, no, it's blocking it. We've never seen it because we don't use it that way. But good point. We will never use it this way. We're gonna have to rethink all this, right? Because if you're trying to use it for forensic localization versus just, is it too hot to be in here? Now you've got problems. So that was a case of where that would have been chalked up as human error, you know, whatever the operator was doing, they were just doing it wrong. And it was really, in fact, the sensor. There was no way the human could have done better, and it would have been hard for an AI system to have done any better either because we didn't understand the correct way to operate the sensor for that situation. So again, the idea is, where do they want to be? The responders want to be far away. They want to be doing in many places at once. So how do we model that? And we really see this as the future, because right now, they typically come out and make their tactical decisions by working directly with the field team, but they really could be doing it from further locations or as they go. So as this becomes, the internet connectivity at disasters, at least in the United States, is getting much better, much faster. You get these cows on wheels, sails on wheels, or what they call, and they actually have shown up about the same time as the actual FEMA teams. So it's becoming possible to have at least reasonable, not great, bandwidth. So how do we exploit that? Well, one of our earliest set of work has been at modeling just how you interact with robots as a set of roles. And so robotics is traditionally focused on either the robot or the team, the 2 team members that are using it. And by the way, if you've got a UAV, you have to have a safety officer there. But now you've got, with the internet, this possibility of your knowledge workers who may not know Is it a robot? Is it a pigeon? A dog? Who cares? Just give me the information. And that creates, they're working back, they can possibly directly, like you saw with Skywriter, tell people what to do or put in requests. They may be able to time this out, so who needs what when. So now we're looking at all this information and data. Probably you're not going to try to do what we tried to do in Katrina. The state of Florida basically said, we don't know what everybody needs. So the Tallahassee EOC started, when everybody got their satellite internet up, they gave all of the high resolution maps for everywhere in Mississippi and Louisiana and broadcast them, bringing the satellite internet connection down. And then it'd come back up, and then we'd do it again. And, you know, and then eventually after about a day of that, they just, Tallahassee is only 6 hours away from the Katrina site, so they would just, every 6 hours, you got a new set of DVDs. And it turned out, most of the responders were like, I don't need a high resolution map, I just need the basic street maps, you know, kind of thing. And so understanding that is a big deal, and why we do a lot of our cognitive work analysis to try and figure that out. Well, so we've got this idea that there's data coming in, and to other people it should be visualized or represented, and there's different times at which people can do it. The tactical responders need it now. Geologists and hydrologists, they don't get the data for 4 days, so if you give it to them in 2 days, they're like, you know, you've cut their time in half, even though that seems rather sad and slow. So each role has a different use. So we came up with a computational model, trying to go back to classic flowcharts. So those of us are kind of having negative flashbacks to the past when we use flowcharting symbols over there. But you know, might as well go with the iconography that we have. So if we think of the robot as providing data, and then there is some display or representative of that data, which is often called information, then the agent, be it a robot, a software agent, or a person, a cognitive agent, makes a decision, and they often bring in their own knowledge and expertise to do that. And in particular, the ones we look at, there's a lot of knowledge and expertise associated with that agent. So that's not too bad. Well, what happens, that what we see is that you've got the data. Well, usually there's the data, but you've got to stabilize the image and whatever, are you displaying the image, and how do you know all the data you've got to search and give the right video snippet to, because you don't want to send 300 images and 1 terabyte of data. So that usually is what we put in the interface and what we're transforming to get to the interface. Then once we're there, the human is looking at this. There's a question mark at this barrier. Do they trust it? Can they even see it? I mean, we typically overload the visual channel. Can they comprehend what they're doing? Have we gotten a decent interface display visualization for them? And can they grab additional beyond their knowledge, which they can use extra information or begin to actively direct the process? And can they grab information like from the Internet of Things, the cloud, what's going on there? And how do they sort through that and sort it out? And so what we've tried to do is also train our observers, and we've created with NSF an open source thing. We're trying to capture all this data coming in and be able to mine and ascertain what's happening at what time. So we tried this out in 2012, and this is a part of Disaster City. So we're going to fly this quad rotor, your basic quad rotor, for the chemical train that you saw with Skywriter. The chemical train is right here, okay? About a mile away is where we're allowed to fly because it was a high fidelity concept of operation. So in chemical spills, you're not going to get closer than a mile until you can prove what the substance is and that the wind isn't going to catch you. Otherwise, you have to suit up. So we're a mile away, and you see about a mile away from here is the Emergency Operations Center. Okay, you're only a mile away. So how long do you think it takes for a tactical responder who's going, yes, we've got a chemical spill, here's this and this, I'm going to send you a picture, you need to see this on the radio, person standing here saying, I'm seeing this in real time, I want to send you a picture because you need to see this. So it felt like the information wasn't sufficient to describe verbally. How long do you want to think that took? State-of-the-art military system, air robot, heavily used by the Army. Wireless networks provided by the National Guard. No.
An
2
hour.
hours.
No, good though. Most everybody goes like 5 minutes, like, well, yeah, 2 hours. No, it was 28 minutes, but even better, it took 4 transformations. You just couldn't do, like, okay, we've got to get the picture and then we're going to do this. It was like, no, you've got to take the picture out. You've got to change it from one proprietary file format to another in the hopes that that'll be the format the incident commander will find. And then you discover that part of the network isn't working, so you'll go ahead and email it on your cell phone. Okay, no, other than that, it's just great. Oh, and then better yet, the observer sitting there said, yeah, it came up in their email and they didn't notice it at all. So we, so 4 hours later we have the iron. Oh, you sent us that? Yes. But don't worry, when we did it again the next day, they got it immediately. You know what? We sent them, the field team sent them 4 pictures. We don't know why. One of them was a picture of just the basic hazards placard that you have, so this is a chemical train. This is like the least useful piece of, whatever. They sent that one of the 4. They had the serial numbers, which are really important, the chemical thing, which are really important. Guess which one arrived first? The stupid one, the one that didn't, because it was the lowest resolution, the lowest bit. So we couldn't even control the priority of that. This year we did a wilderness search and rescue exercise. Once again, we've got full internet access. You're just out in a nice lake. I am literally leaning over, taking a picture on my cell phone of the low resolution display of where we found the survivor with the UAV, because it's got the lat long on it, and I won't have to radio the lat long in because I'm going to screw up the number and just email it to them. Instant message. I text message the thing to it. So it's pretty sad. So the systems are not built as real systems. We're not getting data, we're not getting information they can use. We're hoping like hell they can use an image. We give them too much, we do this post-processing and that. So this is a continuing problem, and we think this is the real challenge in robotics. It's not the robot platforms, they're good enough. It's how do we get the real users, the real stakeholders, the informatics that they need. And we have a nice laboratory. The Respondor system is an open source system. We carry our server in this really nice truck. And besides the fact of having to do maintenance on a 21-foot Freightliner truck, I kid you not, the guys in my lab will not drive it. It's only women seem to drive the lab, my 2 women grad students. And unlike everybody else, do other professors have to deal with dead possums that have died under your truck? Okay, and here's the kind of life I lead. So now that my grad students are texting me, there's a dead possum under the truck. Are you sure it's not plain possum? No, because all the grad students have gone out to poke at the possum. So I feel our productivity numbers are soaring, right? Just absolutely out there. So what to do? Well, I'm not picking up the possum. I'm from South Georgia, but I'm not picking up the possum. So what are we going to do with it? So I call, what else to do? I call the police, campus police. They said, oh, we don't make, Dr. Murphy, we do not know how to deal with this dead possum. But hold on. They come back about 3 minutes later. Very different tone of voice. You should call physical plant. They handle dead animals. She said, you did not know that 3 minutes ago. Do not get smart with me. So we called physical plant, and it sat there for a while. So, which I don't think other professors have to go through some of the things of field work that we do. But anyway, but I digress. So in summary, disaster robotics is really less about the robot and more about the human-robot interaction, how real people, the stakeholders, are engaging, whether they know they're engaging with a robot or not, and how they get that information. When do they get it? Is it in the right form for their unique task and job? Because a disaster will have a minimum of 28 agencies out there. So how do we get that? How do we do it? And how do we capture that? So I think we've made some progress with the viewpoint cognitive work analysis. The field ethnography you know, it's a cheat sheet, but at least it's something to try to standardize it. And then that computational model of the D2D process, we're going to continue to push on that and see if that buys us something in trying to formalize how we capture what the transformations are that needed. And I'd like to just end with inviting you to join us for our Summer Institute. Every year we go out and play at Disaster City. This year we're doing, it's our second year of working on flooding, both swift water and storm type surges. So we'll be flying UAVs, we'll have water vehicles, we'll be doing house and building inspection, bridge inspection, underwater inspection, trying to do debris, hydrological state of the coast. And we'll also be doing some crowdsourcing, so we're going to be split between Galveston, where we'll be doing the storm surge, because Galveston got wiped out by Ike, and so anything that sounds like it's going to help them with flooding in the future, they are so on that. And we'll be also doing crowdsourcing of different drainages there. Then we have Disaster City is where the EOC is, so they'll be doing a full EOC, like during what would you be doing if you're one of those people in charge of a disaster. And then Corpus Christi will also be doing some crowdsourcing and also flying along their area of the coast. And we'll be flying and running robots over at Riverside as well. So we'll have 4 sites in play for 2 days of exercises. One day focusing on these agencies like the Coast Guard. What are you doing the day of for the first 24 hours? Then what do you do with all that debris that's left over? How do you ascertain that? How do you figure out what's going on? And so hopefully you guys can play, and I look forward to working with you. It's so wonderful to be here. You are just such leaders in the field, and it's great to be here. Thank you very much, David.
Thank you. Go for it.
So, I didn't know much about disaster robotics, but robots can do 2 things. They can sense and they can act. It seems that at least the current state of the art is just more on the sensing part, that they're not actually very active on acting on whatever they find. It's just serving as cameras and maybe temperature sensors or something?
Or radiation sensors, yeah. Yes.
They're not really kind of acting or intervening.
Autonomous, you mean?
Autonomous, or even
just acting. No, so they're seeing, perceiving, and acting at a distance. They're primarily, you are absolutely right. They are primarily used for perceiving at a distance. They can be used for acting at a distance. They were using them to drop off sensors, turn valves, try to open doors at Fukushima. They were essential in the BP oil spill because they were turning valves, discovering that wasn't working, doing that header, and then lowering and putting down the cap over the BP oil spill, over the Macondo spill. And then the 2 ROVs, they have 1 ROV, it always takes 2, one to do something and one to give the actual view of what's going on. And they bumped into each other, knocked it out, and they had to reinstall it a week later. They don't mention that as much. Okay, but you're right. Now remember, one of the fairness to the little critters and the underwater stuff is very common to pick things up. For instance, that ROV that you saw the arm there, that's part of a system that was built for the UK, where the water's really cold. And so they believe that if your car goes off into the icy water, they've got 60 minutes to revive you. So if they can have somebody, the policeman can just throw this, so simple, even a policeman can use it, that is their words. That's not me denigrating, but throw it in the water, get it to them, cut their seatbelt. They have a little thing that breaks the glass, cut their seatbelt, and then just grab, and then it grabs on, and then you pull on the cable on the ROV and bring them up. If you can do that in 60 minutes, there's a good chance you can revive them without brain damage. In the United States, less clear. The people in Boston are good. You know, you guys probably not so much here. And in the Gulf Coast, our water temperature never drops below 70, so that won't work. But, so we do it. It's just rare. It just depends on the mission. UAVs, small things, can't do much because they're small. They don't have much force. They have no way to leverage. But good point. Good call. Okay.
So great talk. I loved it. So you talked about moving from the in-person, face-to-face contact with other individuals and with the robot to a distributed setting, and you talked about trust issues. But what about other kinds of human issues that would be introduced in this distributed setting? For example, communications. What kind of impacts on communication exist you know, how does this affect the one-way, two-way? So can you talk about that?
It's horrible. Isn't it going to be terrible? We're moving people co-located. We know, in general, your only hope of getting people on the same page is to have them co-located, get to see each other. We're not going to have that luxury. So how do we develop computer systems that can minimize the negative impact and can make, you know, at least break even? So the idea of the visual common ground, at least we may not know each other, we may have a protocol to say hi to each other, whatever, but try to get at least focus on the task part. So we don't have to try to use the fact that we don't have the signaling and the grunting and all the stuff that we would normally have. We're deprived there, but at least we've got the audio and the touch part with the visual common ground there. But it's going to be a problem. And the emergency responders are like, look, we've got chat rooms. Now we don't even have to do roll call or introduce anybody. And it's like, I think actually that's actually a kind of an important part, probably the most important part before going out in the field. We were for Hurricane Charley, big room right before we're deploying for Florida Task Force 3. And police officer looking at me like, where the heck did they find me? I'm used to that, but that's okay. All right, and then I'm trying to figure out who, I've never seen that person before that. Well, once it went around the room, and then when I said, I'm Robin Murphy, I'm the professor over at USF that does the rescue robots, and they were like, oh yeah, you were at 9/11, yeah, okay, great. And you know, you could see all of a sudden it was like huge amount. And you could also hear, so one of my PhD students in industrial organization psychology, Jenny Burke, was sitting there at the EOC and said you could hear people say, oh yeah, I know that person. Come over the radio, listening, kind of lurking and vouching as you're making these connections in real time. And so we're very concerned that computer mediation is taking that away. But at the same time, it's inevitable. So how do we do it? So that, I look at that as your problem, actually. See, I have found disasters, you know, yeah, and nothing you did. It's a hard one. Okay, in the back first.
Is there a need to coordinate the aerial robots to other means? For example, in 9/11, I imagine that there will be helicopters all the way carrying people and equipment, so you can just say, please stop the helicopters for half an hour because you need to fly. It's nice.
Oh yeah. Yeah, you've hit a deep well there. Okay, so when disasters happen, normally a temporary flight restriction is put into place. And that's to allow the manned helicopters to operate safely and work at about 200 feet. That's when they do those hoisting to rescue people or to just drop off responders directly into there. They're extremely vulnerable. Their rules, and this is pretty much everywhere in the world, if you see something that's not supposed to be there, you have to immediately cut your hoist and fly back until somebody gives you approval. So you've already lost about an hour. Just somebody, oh, well, I've got a UAV, I can help. Okay, besides the fact that a pigeon can take down a helicopter, and with the LiPo batteries on these different platforms, it's an exploding pigeon. So it's not just a pigeon, it's one that goes into flames. So probably not the best thing. So we have a real problem with that, unfortunately. But there are ways, all you do is you can, with a temporary flight, if you're flying under permission from the incident commander, and I don't get to go unless the incident commanders, I have official invitation, and that also covers liability. There's also, you show up basically at dawn, everybody, all the air people show up at dawn for the air branch, check in with everybody. That's again, the same thing where you look at that. The National Guard for us at Possum, it's like we were thinking they were going to be mad. They were like, oh, UAVs, about time, man, because you guys should have had that. They were looking over at the Washington State people. So the National Guards were like our best friend. They were like, yeah, you can coordinate. Yeah, you just stay over there and we'll do that. Well, if we drop below 500, we'll call you on the radio. And if you don't call, we'll, as soon as we see you, because it's hard to miss a helicopter, large helicopter, we will land in 1.5 minutes. We guarantee we will never be more than 1.5 minutes away from landing. So it's called rack and stack, probably what you want to know. But you can do it. It takes somebody being aware of the rules. So in Haiti earthquake, Haiti immediately did a temporary flight restriction. So the US wasn't flying any helicopters in initially. They were flying a Predator, Haiti small, so it's pretty easy to just fly around on the outside of their airspace. figure out what the heck's going on, so that anybody who was having to coordinate until they could figure out what's going on with that airport, which is the only way in and out. All the ports are messed up. They do not know the state of the ports. You just can't drive big ships up unless you want to sink your big ships of supply. So it took them 2 weeks to reopen the port. Okay, great. So go team. One group goes down, self-deploys, and nobody says, look, we'll be happy to fly small UAVs for you. Anybody, all you need to do is pay $3,000 a day for our services. And so there were no takers. So they flew anyway just to show that they could get that. And it's like, please don't do that. Just you get it shut down for everybody. So anyway, that was probably more than you wanted to know about UAVs and disasters. But I told you it was a deep well that you were getting into. Gary, you have.
You mentioned the thing about training, that the military is willing to put a lot of time into training people to work these things, whereas the fire, police, their workload. But I would think that there'd be some incentive, realizing the value of this, to kind of rearrange some things, because it's like a new thing hitting their work load. But long term, it's going to be something really useful. So is there some priority or some incentive to introduce more training of this as opposed to something else, or is that just not possible?
That's so cute. No, there's no incentive. The system is full of disincentives.
Can you repeat the question? We couldn't hear it.
Okay, so the question is, so these are clearly, let me paraphrase. These are great things. It seems like there should be some incentive or way for these groups, these agencies to do the training. Suck it up, go ahead, start planning. In all fairness, they are trying to plan, but the technology is moving very fast. And then second, it's expensive, so that training. So the only reason why bomb squads have bomb squad robots is because the National Institute of Justice said, dudes, you will not be listed in the FBI's official registry of bomb squad robots unless you have bomb squads, unless you have a bomb squad robot. And this turned out to be even more important. We are setting up enough money for every municipality that currently has a bomb squad to buy at least one bomb squad at current prices. This money will be guaranteed for 5 years, so you can buy now. You can buy any bomb squad robot that's currently made. There were 3, big, large, and heavy, okay, or any other one that meets the following requirements, which were pretty broad. And so all of a sudden, those 3 companies got swamped by lighter, more agile. By the end of the 5th year, you had beautiful robots that were actually useful instead of sumo time. And the FBI had set up training course, and part of that is that they had the money to go to Huntsville for that training course. So they set aside all the money and made that in there. Until we have that happen with some of these agencies. And remember, it's not just the fire department. We've got EPA for a chemical spill. You've got all sorts of groups. So how are we going to do that? So until we get the money and sheltering on how they do it, I don't see that happening. And they know it, and they're trying to lobby, but within the DHS system. But that's the reality there. So, on that, I've just kind of depressed you about disasters even more so.
This is not my question, it's his question. He wanted to know what are some of the capabilities of robots in the future as far as the disaster recovery is concerned.
Well, I think the nice thing about robots is that you're going to start seeing more and more data. Like right now, they can already create those 3D visualizations, so you can actually create a 3D elevation map, and the hydrologist can go through like they're in a video game through the world, and it's pretty accurate with all the video overlay. So that's a very nice thing that we're going to see. The other thing is you're seeing the robots are becoming more agile. So it's you're beginning to see things like, remember that movie Big Hero 6 with the blow up? Well, some engineers have finally said, this whole kind of way, it's just not working. So what if we do and have Big Hero 6 like marshmallow around something and turn it, and they go, let go of it and go. So we're going to see some really great improvements in that. And also we're seeing snake and caterpillar robots that actually work in rubble, in dirt. And one of the biggest things that we're going to see in the future that I hope soon is is we're gonna have little windshield wipers like they do in NASCAR, because right now, all the robots, they're down. You're thinking of a robot's gonna be, a ground robot's gonna be about the height of a squirrel, height of a mouse, going through dirt with no eyelets, so they just get dirty. You pretty much get dirt all and mud all over it. So we're gonna have better equivalent of eyelets. Those are the things I think are gonna be in the near future.
What about interagency policy paralysis?
What about it? Let's give it up for interagency paralysis. Yeah.
Well, it strikes me that there's just a boatload of federal agencies especially that love to make rules to prohibit doing things. And if you're in a disaster situation, what might seem to be the sensible, common sense thing to do to pull a person out of the fire might in fact contravene any number of policies about smelt in the California Delta, or conifer seeds and their proliferation across, whatever.
We don't care if it's the last horned toad. Yes.
Yeah. Well, horned toad is a great example. So, to what extent do planners worry about contravening rules?
Well, you know what, we're not finding as much on deployment, because when we do our exercises, we'll have the city managers, we'll have like the insurance companies, the commissioners, DPS, and the Bush School, and things. What we're finding out is like the FAA really hasn't been as big a hassle as they for emergencies as you would think. The FCC is actually harder to deal with. The bigger challenge has been some inadvertent regulations that prevent. We found that a building, a multi-story building, or a building for a hospital or a school. Schools are considered the canaries of whether an area has come back, because nobody's going back to work until the schools are open, until the kids are in. Okay, so you want to get that up and running. Well, that building will have been inspected at least 4 times. The USAR people will have walked by it. Most of them are structural specialists. But they are regulatory not allowed, listed on that county's list of approved inspectors. So they can't inspect it, even though they just did. Right? Then you bring the next group in, and the same thing. And the Red Cross comes by, because nobody ever tells them anything. And they're trying to second guess, so they try to sneak in and figure out what's going on. Literally, they do like these surreptitious driving through type thing. So you get this until you finally get somebody. You have to wait until the county inspector, which there may be one, right, who's got to do all of these. So it's a bigger problem there. So that's an unintended regulation. Another one is we don't know how to share because we never had to. Emergency response is divided into 15 or 16, depending on what state, emergency support functions. And the basic idea is that a disaster happens, the fire rescue people go do fire rescue stuff, the police do cordon off and block off and try to evacuate people. And then maybe about the 12 hours, certainly about the 24-hour mark, everybody will get together. But you just assume they're doing, so because what would you tell them anyway? Well, and the same thing with the geologists and hydrologists, the responders at ESF 9, which are the search and rescue, pull people, all the rubble people are working while the geologists and hydrologists at the ozone mudslides are trying to figure out what the heck's going on. And oh, great, the river keeps forming and damming and breaking the dam net. They're working. And it wasn't until like the next day they realized, wait a minute, the data we collected for them could have been used for them too. And they're in the same building, right, at the end of the day, at the EOC. And they have, how are we going to share? It wasn't a regulatory prohibition. It's just they had never had to work together, and just how does that do? And then now we've discovered it at one place. So I came back and told the guys at Disaster City Teaks, these are all like famous firemen who are instructors, and they said, "Oh, great! We just got the National Incident Management System, which said you have these 16 functions. Now we've got to go back and train them on how to talk to each other and share data." That'll be another 15 years. This takes time. Did I even vaguely answer your question? I'm sorry.
Well, you told me that my question was totally irrelevant until we could share data.
Yeah, the sharing data is probably the biggest one. It's probably the biggest one. And it's not because of regulations. There are some inadvertent ones. Those can be, as soon as you identify them, the Bush will say, if you just get a list of what's, this, you can share it. Likewise with the insurance company, the insurance commissioner was like, oh, we fly predators in Texas before a hurricane 2 days before. This is common in both Florida and Texas. And we fly them immediately after. So that would be like all the damage data. You could kind of get a rough estimate on it. Yeah. So, oh, and I bet we could share that with all of the insurance companies that are there. It's like, and he doesn't need a regulation because he owns it as the state commissioner, but had never thought of it. Never had made sense to him before. So part of it's just informatics, getting the right information, in this case, to the people ahead of time and start thinking about how they can do their planning.
I think I would summarize your talk by saying real world problems are gnarly. And there's just so many details and things that you can't expect when you're working with abstractions for solutions. It's a reality check, I think, that you gave us on real world problems, but a lot of interesting challenges there. So.
And well worth solving. And these are
Yeah.
things that you know how you're working on these problems. We need you to work on these problems and to not give up hope because some of them, because they are gnarly, or if they say at Huntington Beach.
All right, let's thank Dr.